This is the explanation for expansion patterns, section 2A in your textbook. We're going to go through 4 different expansion patterns: the distributive law, product of 2 binomials, difference of squares, and perfect squares. The rules behind expansion are exactly the same in all of these cases, and that is that when you multiply everything here by everything in here. And we do that no matter what type of expansion we have. Normally, if we were going to multiply these with numbers, then we would follow bedmass laws. If I had 3 times 2 plus 5, then I would first add 2 plus 5 together to get 7. My computer, and then multiply it by 3. So 3 times 7 is equal to 21. But when I have algebra, I often can't add these two together because they're not like terms or for whatever reason. So if I can't add them together, then I have these possibilities with the expansion patterns of still being able to do something with the algebra expression and be able to come up with a simplified version or something I can use in another situation or depending on what I want to do with it. So the first one is the distributive law. When I distribute something that is outside the brackets, in this case it's just a single term, it's just an A, there's nothing like here where I have 2 terms, it's just a single term, then just take that term and multiply it by the first part of the brackets and then multiply it by the second part of the brackets. So we write that in general terms. For any number outside the brackets, we take A times B and then we add it to whatever A times C is. So that's the expanded version of this multiplication. Let's look at a couple of examples. If I have a negative sign on the second term, or in this case it's a subtraction sign, then think of this as adding a -1. So when we're working with it algebraically, then we like to keep everything as addition. So subtraction is interpreted as just adding a negative. So you can think of it like that. And then we take 2 times 3x, that's going to give us 6x, and 2 times -1, or we should think of it as 2 times -1, gives us a -2, so we write that as -2. And that's the expanded version. If I have negatives in other places, I still follow the same rules. Let's take one where the negative is on the outside, and maybe even one where there's also a negative or a minus sign on the inside. And I take the outside of the brackets. -3x times x is -3x squared, and -3x times -2 is positive 6x. Okay, that's the distributive law. Let's move to the product of 2 binomials. This is called a product because it's the answer when I multiply these 2 things together. And binomials are bits of algebra that have 2 things added together. So this is one term, this is another term, and so that's a binomial because there are 2 terms. Same with this. 2 terms, so it's a binomial. Over here we had a monomial because it was just one term times a binomial. And this is called the product of 2 binomials because of these two brackets. Sometimes people call this FOIL. You might remember that. That stands for first, outside, inside, last, just to keep everything in order. Some of my other students in the past have called this the rainbow method. First this one, then this one, then this one, and then this one, and it kind of starts to look like rainbows all over the place. It's just to keep the order of multiplication in place. So A times C for our firsts is AC. A times D is AD. B times C is BC. And B times D is BD. Okay, the point of that was to multiply everything in this bracket by everything in that bracket. Let's look at some examples. X plus 4 times x minus 3. So first x times x, the first ones together, the first in each binomial, and the outside terms, so x, remember this is a negative 3, so we get a minus 3x. Negative times positive is a negative. Plus 4 times x is going to be plus 4x. And 4 times negative 3 is negative 12. In this kind of expression, there's often two terms that you can add together. We have two like terms. They're both terms with the variable part of x. So we can put them together in a final statement. X squared minus 3x plus 4x is just 1x. So we write plus x minus 12. And that's your answer for expanding that. Okay, works the same even if I have more complicated brackets. So sometimes I might have something like this with a negative sign, or actually let's even put the minus x second. So I'm going to do 3 minus x. Just put it onto the page. Okay, 2x times 3 is 6x. 2x times a negative x is a negative 2x squared. Minus 5 times 3 is minus 15. And minus 5 times negative x, that's a negative and a negative, that's going to be positive 5x. Now I have to look carefully for the like terms. Can we squeeze the x in? Look carefully for the like terms. This is x squared. That's a constant term. But these two here, the 6x and the 5x, are like terms. Make sure the sign you use is the one that comes right before the number. So this is a positive 5x because it has the plus sign in front. Let's write the x squared term first with the highest power on the x. So negative 2x squared, and then 6x plus 5x is plus 11x, and then minus 15. Okay, that's done. Feel free to rewind and look at anything again if something wasn't clear. We're going to go on to the difference of squares. This is just like multiplying two binomials, but it's a little bit special because the first terms are exactly the same. The second terms are exactly the same, but the signs are different. This one is being added and this one is being subtracted. It's called the difference of squares because of what you end up with. When I multiply this out, I get a times a, which is a squared, just using FOIL again, or the rainbow method. A times negative b is minus ab. B times a is ba, but let's put the variables in alphabetical order as we usually do. So we'll write this as plus ab. Doesn't matter what order you multiply things in, so ba is the same as ab. And then b times negative b is a minus b squared. And what happens is the middle two terms, which are like terms, one is negative and one is positive. And when you add them together, they cancel out. It's like having a minus 3 plus 3. That's going to give you 0. So I get a squared plus 0 minus b squared. And here's your difference of squares. It's a difference because it's subtracted. That's what difference means. It's the answer when you subtract. And I have two squares, a squared and b squared. So we could even put in here, it's the difference of two squares, a squared and b squared. And in fact, this happens so often, this comes up so often, we just write it as a single pattern here and memorize that as a pattern, so we don't have to do the FOIL all the time. We can take the shortcut. When we have exactly this setup, two identical numbers out in front, two identical numbers at the back, one with a plus sign, one with a minus sign, we can simply write the first one squared minus the second one squared. So let's take a look at an example. X plus 4, x minus 4. I could do this by FOIL and multiply everything out and add like terms together, but I recognize this. X, exactly the same. 4, exactly the same. One positive, one negative. That's very important, otherwise the middle terms don't cancel out. If they're both positive, it doesn't cancel out. If they're both negative, it doesn't cancel out. One positive, one negative. that's just going to be x squared, square the first term, and then minus 16 squared. 16 is already squared, it's 4 squared. So x squared minus 16. If you want to see where that come from, we took x and squared it, and then we subtracted 4 and squared it to get x squared minus 16. You can do the same thing even if it's a little more complex. Again, one is negative, the other one is exactly the same term, but it's got a plus sign in between the two terms. So 3x times 3x, that's our first term. That's going to be 3x squared. So let's write that in brackets like this. Minus, here's the last term is 2, so that's going to be minus 2 squared. And I can figure each of those out. This is 9x squared, and 2 squared is 4. And that's the final answer, 9x squared minus 4. Okay, our last pattern is a perfect square. This is the same binomial squared by itself. And lots of students, this is wrong, don't do this, but let me show you what's not okay. Lots of students just square each part and say, that must be the answer to that. I'll square A and I'll square B. But that doesn't work because when we do, if we remember multiplying binomials, when we're doing two different binomials, we can't just do A times C and B times D. That doesn't work. We have these middle two terms here that also become part of it. So when I multiply two binomials, I always end up with 4 terms. And that's no different when the terms are exactly the same. So it's not okay to just do that. So what can we do? Well, if we write out what this squared part means, it means take A plus B and multiply it by itself. So that looks like FOIL again. Yeah, just like we did the rainbow method the page before. So A squared plus AB plus BA. Oh, let's write that as AB so it's easier to add together. It doesn't matter what order if we're multiplying. So plus AB plus B squared. What you notice here, unlike the difference of squares, these two terms don't cancel. They're exactly the same, so they add together. And I end up with A squared plus 2AB plus B squared. And that pattern always comes up no matter what you put in for A. Even if you put in 3xy squared, that will still be multiplied by itself. Then twice this term times this term, and then the last term squared. So it's almost what students want to write. We've got the A squared plus the B squared, but we also have this middle term where we take that, multiply it by B, and then put the 2 out in front. So again here, we're going to erase the workings, and we're going to work on memorizing this pattern so that we can do expansions a little easier and not have to always do FOIL. So this is A squared plus 2AB plus B squared. If you subtract instead of add the two terms and square it, you get almost the same thing, but those two middle terms are going to be negative AB and negative BA rather than positive. So the pattern for subtracting and then squaring a perfect square looks very similar, but the middle term is subtracted instead of added. Okay, how can you use this? Let's look at something like this. 2x plus y, sorry, not 1 squared. In my pattern, I take the first term and square it. Well, that's 2x. So let's square 2x. It's adding, so I'm going to use the first pattern. Plus 2 times the first term, which is 2x, times the second term, which is 1, and then take the second term and square it. That's 1 squared. So I treat this part is A, and this part is B, and then I plug into the pattern. Still have to multiply this out. 2x times 2x is 4x squared. 2 times 2 times 1 is 4. A single x. And 1 squared is 1. Okay, let's do another example using the pattern. So let's do 3 minus 2y and square it. Now I don't have the pattern in front of me, but I've used it so much I can remember it. Maybe it's helpful to just write it here for a minute. A squared minus 2ab plus b squared. This time I'm using the minus, the subtraction one, because there's a minus sign in between the terms. So my first term is 3. So we square that. Then we subtract 2 times the first term times the second term, and then add the second term squared. Erase this so I have a bit more room. 3 squared is 9. Negative 2 times 3 is negative 6, times 2 is minus 12 with a y. And here I have 2y times 2y is 4y squared. Okay, and that's the answer. Takes a little practice to be able to use the perfect squares expansion especially, but it's worth it because you get faster at it, and it's also a good algebra conception to be able, or a good concept to hang on to be able to see this pattern as sort of envelopes to plug things in. Yeah, A is just holding the place for whatever A is going to be, and A could be a single number or it could be a bunch of things, right? Here it's just a single 3, but B is 2y. So I have in my pattern, I have A equal to 3 and B equal to 2y. And it's good practice to be able to do that, to then plug in the whole 2y in for this variable in the formula or in the pattern. Okay, it's time now for you to try some of the homework, either now or next class if you're watching this at home. Good luck. Hope it goes well.